So even though I said, where did I say it? The exponents in the rate law are not related to the stoichiometric coefficients, even though sometimes they are numerically the same, which is very confusing. The exponents in the rate law are related to concentration and the rate of the reaction. So even though they're not related to coefficients, the exponents in the rate law are related to the rate of the reaction and the concentration of the reactant that they are associated with. And this relationship is really powerful in terms of helping us determine all kinds of kinetic information about a reaction. So we're going to look at 3 examples of this relationship. The first one that we're going to look at is rate equals K A times B. So this is a very simple rate law. It's first order with respect to A, it's first order with respect to B. And let's just say that the value of the rate constant K is 1, just to keep it nice and simple. And we're not going to have any units at all, again, just to keep it nice and simple. And what we're going to do is consider running this reaction 3 different times. So we're going to run the reaction a total of 3 different times. And in these 3 different times that we run the reaction, we're going to make changes to the concentration of A or B. So let's say initially we start the reaction with a concentration of A and B that's equal to 1 molar. If we had 1 molar A and 1 molar B, what would the rate of that reaction be? To solve this, we're going to use the rate law, K times A times B, and we're going to use the value of K, which is 1, and the value of A, which is 1, and the value of B, which is 1. So the rate for this reaction would just be 1. Pretty simple, right? What if we ran on trial number 2, we ran the reaction with 2 molar A and 1 molar B, and what would the rate be in that situation? And again, we're just going to be plugging into the rate law. K is 1, now A is 2, B is still 1. The rate of this reaction is 2. So we can see that when we doubled A, so we went from 1 to 2, we doubled A, our rate doubled. It also went from 1 to 2. What about, let me try to get really tricky here, number 3. We kept A at 1, but we doubled B. Ooh, what would that be? Well, again, K, the rate constant, is still 1. The concentration of A is 1. The concentration of B is now 2. And so that means that the rate is going to be 2. And again, we can say if we're looking at the data from trial 1, comparing it to the data from trial 3, when we doubled B, we doubled the rate of the reaction. Look at that. This is actually really simple. So if you feel like maybe you're missing something because it seems really easy, you're not. You're not missing anything. This is just nice and easy. Let's try to make it a little bit harder. So let's look at a more complicated rate law. Let's say that we have rate equals K A B squared. And again, we're going to make K equal to 1 just to keep it nice and easy. And we're going to do the same thing. So we're going to consider running this reaction 3 different times, changing concentrations of A and B, and looking at how that affects the rate. So we got 3 different trials here. And let's say that we start with a concentration of 1 molar A and 1 molar B. What would the rate be? Well, again, our rate is going to be K, which is 1, times A, which is 1, times B, which is 1 squared, still just a rate of 1. What about if we kept let's double A, so it's 2. We kept B the same. What would that rate be? Well, K is 1, A is 2, B is 1 squared, so doubled. And we can look at, if we look at, we've doubled A, we've also doubled the rate, just like in the example above. No change being made to B. So let's consider third trial. Keep A at 1. We're going to double B, so B will be 2. What will this rate be? Our K is 1, our A is 1, our B is 2 squared, boom. So the rate is 4. So what's happened in this situation? Well, now if we're comparing trial 1 to trial 3, when we doubled B, we went from 1 to 2, we quadrupled the rate. We went from 1 to 4, and that is because of the exponent associated with B. So doubling B has a quadruple exponent, a quadrupling effect on the rate of the reaction because of that exponent. Let's look at one more example. This, we're going to look at rate equals K A B to the 0 with a rate constant of 1. B to the 0, that is a possible but I didn't really go over possible values of the exponents, but normally they're whole numbers like 1 and 2, but it is totally possible to have 0. We call this 0th order. So this particular reaction, we would say it's 0th order with respect to B. Overall, this reaction is first order. 1 plus 0 is first order. So what does it mean to be 0th order? Well, let's go through our trials again. We're going to run 3 trials of this reaction, and we will look at how changing the concentrations affects the rate. So let's say we start with concentration of 1A and 1 for B, and what would the rate be? The rate is K, which is 1, times the concentration of A, which is 1, times the concentration of B to the 0, which is 1. If you can't remember how to do, something to the 0th power, you can always plug it into your calculator. So now let's double A. So A is 2 and B is 1. What will that rate be? The rate is K is 1, A is 2, B is 1 to the 0. So that rate is going to be 2. And this should be starting to really see this. For first order, if you double the concentration, so when we're first order with respect to A, when we double the concentration, we double the rate. So now let's consider option number 3. We keep A at 1, we double B. So now B is at 2. And how is this going to affect the rate of the reaction? Well, the value of K is still 1, the value of A is 1, and B is 2 to the 0. Go ahead, if you don't remember raising something to the 0th power, plug it into your calculator, the rate is going to be 1. 2 to the 0 is 1. So does that make sense? Well, if we are 0th order with respect to B, what does that mean? It means that that particular substance does not have any impact on the rate of the reaction. It doesn't matter how much we have. So for B, it does not matter if we have 1 molar or if we have 2 molar, it's not going to have any effect on the rate of the reaction at all. Isn't that awesome? So how can we actually use this type of strategy that we're looking at here? How could we actually apply this? What is the rate law for some reaction? We're going to call it A plus B goes to C. And in order for us to solve this reaction, we need some data, just like we were just looking at. Only this time, the data is all going to be provided for us. So we're going to have 3 sets of data. Sometimes you might even have more than 3 sets of data. And you're going to have concentrations of A, so we're going to say 0.2, 0.4, and 0.2. And B is going to be 0.3, 0.6, and 0.6. And then we're going to have rates, 0.127, 1.02, and 0.254. So again, unlike the examples that we were just doing up here, in this type of problem, you're given this whole entire complete set of data, including the rates. So you have all of this data provided to you. And you need to use that data to calculate the rate law. When somebody asks you calculate the rate law, it just simply means that you are going to be solving for the exponents in the rate law. So we know that our rate law is going to have some sort of general form like this. Rate law always has this same general format. It's always rate equals K times our reactance raised to some sort of exponent. We don't know what it is. And so determining the rate law means that we are solving for X and Y. We're not solving for anything else in the equation. We're trying to turn it into something that looks like this guy up here. So how are we going to do this? Well, our goal is, let's just, kind of go one at a time. Let's focus on X first. And what we want to do is go over here to our data, and we want to find two trials, like 1 and 2, or 2 and 3, or 1 and 3. We want to find two trials where we have changed the concentration of A, but we have not changed the concentration of B. So to solve for X, we are going to look for two trials where A changed and B was constant. Because what we want to focus on is looking, like isolating just the change in the concentration of A. We don't want to also look at trials where B was being changed at the same time. We want to be able to know that any change to the rate is totally due to the change in A. So we're looking for two trials where A changed and B was constant. We know that we're going to need to use trial number 2 because it is the only one where A is 0.4. And then we're also going to want to use either 1 or 3. We want A to be different, but B to stay the same. So that means we're looking for this trial right here. We're looking for two trials where B was constant, but A stayed the same. And then we want to analyze what actually happened in this reaction. So when we went from, to me, in my brain, it's going to be easy to think about comparing trial number 3 to trial number 2. So when we went from 3 to 2, we doubled the concentration of A. When we went from 3 to 2, what did we do to the rate? It looks like we quadrupled it. So when we went from 3 to 2, A was doubled and the rate was quadrupled. Where did we see that? Right here. It looks like right here. In this one right here, when we quadrupled the rate, it was because we had this square term in the exponent. So that tells us that A is second order, or the reaction is second order with respect to A. What about our B term? Actually, I'm going to write this over here. Ka squared. Let's see if we can figure out B. So to solve for B, or to solve for Y, this time we want to look for two trials where B was changed and A was kept constant. So we're looking for two trials where B changed and A was constant. And maybe it's easier to look for the trials where A was constant. So trial number 1 and trial number 3, A was constant. It was 0.2 for both of those, and B was changed. So these are going to work. So now we have to ask ourselves what happened. Well, when we went from 1 to 3, we doubled the concentration. When we went from 1 to 3, we doubled the rate. We doubled the concentration, we doubled the rate. We've seen that one many times. That is first order with respect to B. Now, if you are feeling like, oh my gosh, I really am confused by this. Everything was making sense up until now. That's really normal. You just need to see a lot of examples, and then you're going to start picking up on the pattern, and you will have this down in no time. So let me just emphasize, so the answer to this question, we were asked to come up with the rate law. The answer to this question is rate equals K A squared B1. That is the rate law. And let's do some more examples.